In our last two videos, we looked at how we could use the symmetric difference quotient to approximate the derivative at a point given a table of values, of x and y values, and then also how we could do it given a graph of the function. Now, what if we were given a formula for a function? How could we approximate the derivative? So actually, you should be able to figure this one out. So we could use a similar technique to what we just did. So let's look at an exercise here and see if you can do this one. Let f of x be 3 times x to the x power, and we want to approximate f prime at 2. So using what you've learned before, see if you can figure out how to do this one on your own. Let's work it out now and then come back when you think you have an answer. Press pause now. Well, once again, what we will use is a symmetric difference quotient to approximate the derivative at the point. So this time we have the exact formula, and will also allow us to use calculators, let's say. So recall that the symmetric difference quotient is given by this formula, f of x plus h minus f of x minus h over 2h. So notice 2h is delta x, and the numerator is delta y. Now, later on we will learn some shortcuts that we can apply to this, but notice if any of you have had some calculus before, you cannot apply the power rule, because the power rule applies when you have a variable base and a constant exponent. Neither can you apply the exponential rule, which works when we have a constant base and a variable exponent. So this one has a variable base and a variable exponent, and it was chosen for that purpose so that we can't use any shortcuts like that. We will actually learn a shortcut in our next unit, in our next playlist. We'll talk about how we can find an exact value for this. But for now, we don't want an exact value, we just want an approximation. So what we can do is use this formula where h is 0.001, for example. Now notice, since we have a calculator, it's not going to be that hard to do this with a very small h. So for example, if I were to do this by hand, I might choose an h of 1 and try to do this, look at evaluating this function at 3 and at 1 for the numerator. But I can get a much better approximation if I use a smaller h value. And I picked one that a smaller h value is going to make a significant difference here. So, since we have our calculator, we can do this like this. So, our formula is 2 plus h to the power 2 plus h times 3 minus 3 times 2 minus h to the power 2 minus h over 2h. And we can evaluate this at various values of h. So, for example, if we use of h of 0.001, this becomes 2 plus 0.001, or in other words 2.001, to the power, same power, 2.001 times 3. And this is 2 minus h is 2 minus 0.001, which is 1.999. And we're going to raise it to the same power. In both cases, we multiply by 3. Okay, we subtract those in the top, and in the bottom we have 2h, or 2 times 0.001, or 0.002 if we'd rather. Now at some point we're going to put this in the calculator, so on the screen here on the right you can see what this looks like on a TI-84 calculator. Notice that a horizontal fraction line is a grouping symbol, so we need to be sure to put parentheses around the entire numerator and around the entire denominator, because this division symbol here, this little slash, or the way it looks on your calculator screen, the little line with the 2 dots, that kind of it means division, but does not mean grouping symbol. Whereas a horizontal fraction line means division, but it's also a grouping symbol. So if you look here, you can see exactly how this is typed into the calculator, and we get a derivative of approximately 20.31778045. Now all these digits may not be accurate, but the first few I'm sure are pretty close, or are good actually. So at least in theory we should be able to do this. The smaller h that we put in, the better value that we get out of it. So for example, if we pick an h of, let's say 0.8 and say 5 zeros and a 1, then we just simply change that in our problem up here, so it becomes 2.5 zeros and a 1 to the power, same thing, 2.5 zeros and a 1 times 3, minus 3 times, well, if you subtract 0.5 zeros and a 1 from 2, you get 1 point, and you get 6 nines. Okay, so 1.999999 to the power of 1.999999, and so forth, and you work that out. Be sure to change the 8's there, and we get 20.3177665. And if you notice, these agree at least up to 4 decimal places. They round off to 20.3178. And so we know that our first estimate was accurate that far, and in fact this one probably is accurate all the way, all the digits. Now I say f prime equals this. I probably should have said f prime is approximately equal to that. Okay, and so that is our approximation. Okay, let's try another one. Different function and a different x value, but similar, very similar to the last one. See if you can do this one now that you've seen this done. Given f of x is x to the power 2x, approximate f prime at 3. Go ahead and do this on your own. Come back when you have an answer and check it. Press pause now. Well, we should be back now. Let's see. So once again, we're going to use the symmetric difference quotient. We're using the formula f of x plus h minus f of x minus h over 2h. This time the x is 3, right? And the, well, we can pick, and then this is the formula for f of x. So, plugging in the 3 for x, that looks like this, f of 3 plus h minus f of 3 minus h over 2h. Plugging that in the formula, f of 3 plus h is 3 plus h to the power 2 times 3 plus h, minus 3 minus h to the power 2 times 3 minus h over 2h. And then now let's plug in the number of h that we have. So if we use an h of 0.001, you may have used some other choices, but this is the one I chose here. You can see how this works out, and then simplifying a little bit here before we put in the calculator, we get in the numerator 3.001 to the power 2 times 3.001 minus 2.999 to the power 2 times 2.999 over 2 times 0.001. And entering it like that into the calculator is what you see on the right here on this calculator screenshot from a TI-84. And you see that that is equal to 3.059786694, or at least approximately. That's what that is, which is approximately the symmetric difference quotient, which is approximately the derivative. Now we should be able to get a smaller, not a smaller value, but a smaller h should give us a better value. This time I use 0.1, 2, 3, 4, 5 zeros and a 1, 10 to the negative 6th for h, and I just changed that in the formula here, and you can see what I entered in the calculator screen to get 3059.776715. So since those both agreed to 3059.8, we know for sure that both of these are good to the tens place, and this second one is probably good to several places beyond that, probably about as far out as the calculator goes, or nearly that far. In our next video, we're going to see some ways to shortcut this process a little bit using some calculator shortcuts. But before we do that, you should probably practice this a little bit to make sure that you have this basic concept down.